So the keying system in the 1BCG is just absolutely amazing. It sounds like something It sounds like a typical crystal-controlled radio from the 1950s. How were they able to get that kind of stability in 1920, 1921? And let me tell you, this stuff isn't published. This is not found in any handbook. They're using frequency offset keying with a tertiary winding off the bottom of the oscillator. It jerks the frequency up 10 kilohertz with the oscillator continuously running, while at the same time keying the grid leak on the final. So the grid of the final is totally open until you close the contacts on the keying relay. So simultaneously, one set of contacts short the grid leak to ground, making the final operate, and short a tertiary winding on the bottom of the oscillator coil that jerks the frequency up 10 kilohertz. How do you like that, guys, for 1921?
Okay, I kind of glossed over the original schematic in the second video, but let's look at some of the more subtle aspects of the original schematic. One thing that I just noticed is you can see that the grid of the master oscillator is tapped slightly down the coil. This is a good trick with a Hartley oscillator. If you have the tuning capacitor across the entire coil, do you attach the grid directly to the top of the coil? It's the way that most people do it. That's the way I'm doing it with my oscillator. But if you actually tap down the coil a little bit into the grid, it's a good way to control the feedback into the grid, and you can actually start to influence the way the oscillator drifts. You remember that my oscillator drifted. So that's a good trick to remember. Try tapping down on the grid in the Hartley configuration. The other thing that's interesting is C5. What's C5 all about? It's not really doing anything, but you can see C5 here. There's really not any reason for C5 because this point is the high voltage, and the high voltage is going to be blocked by the grid leak capacitor. Why do you need C5? Well, I think they just wanted to keep the high voltage off of the grid components. So think of it as just a coupling capacitor. Maybe they didn't have capacitors that were high enough voltage rating. So this is one way to lessen the impact on C6 and C7. And if you look at these two oscillators, and you didn't have a lot of time to build a transmitter, which one would you gravitate toward? Looks like the series fed oscillator is a lot simpler to me. It has fewer parts. It doesn't require a choke. We hate those chokes. This is the type of oscillator that they selected for the 1BCG. They went with the simpler series feed on the Hartley oscillator. Now I went with a shunt feed. I went with a shunt feed for a couple of reasons. The first reason, because I'm a follower of Ross Hull, who was the main engineer at the ARRL in the late 20s. He was an Australian and came over to the US and really contributed greatly to the early radio handbooks and QST. So he suggests in a modern Hartley you should never be using the series hookup. You should be using the shunt hookup. Now the shunt hookup does some good things. It takes the high voltage off of the tank circuit. So those big coils are just begging for you to put your hands on them and get a DC shock. At least this eliminates that and gets you down to just RF burns. So we always talk about the Hartley oscillator. Let's go through the theory real quick. So this is a simple Hartley. It's a series Hartley. I've redrawn it just for RF. I'm ignoring the power supply. It's a short to RF, so I'm bringing that right around the circuit as a short circuit. Now the center tap coil, okay, or the tuned circuit, is going to act just like any center tap transformer. The ends are 180 degrees out from each other. And when you add a center tap, you've just created two smaller sine waves. You've cut the voltage in half if it's a perfect center tap. And believe it or not, it doesn't have to be a perfect center tap on a Hartley. We're going to be fooling with this tap, as we'll see. So the valve, we know, provides a 180 degree phase shift from grid to plate. We know that. So with two 180 degree phase shifts, this one here and this one here, we come around and form 360 or 0 degrees, and we have that condition for oscillation. A 0 degree phase shift and a little bit of gain to keep the oscillation going. So changing this tap position changes the amount of feedback. So that's basically the Hartley oscillator in a nutshell. So let's look at the two types of Hartleys as I applied in my version of the 1BCG. I'm not being faithful to the original schematic, so that's a big sin against me. I'm not going for absolute authenticity. In my study, I was looking at keying, trying to improve the keying of the system. So the original series feed design, you can see it quite easily in the simplified schematic. How we have the center tap. It's not shown adjustable in this, but it is adjustable, of course, in the real thing. And we have the drive, which is adjustable. Now look at the shunt version. And look at all the red things. The red things mean that we have B+. Now, on the original circuit, almost anything you touch is going to give you a shock, a DC shock. 2,000 volts worth, by the way. It's not going to be good. But on my modernized design, I'm using shunt feed both on the oscillator and shunt feed on the power amplifier. And this eliminates the DC off both of the tank circuits. So that's a little bit of 1928 technology that I've put into the 1921 design. The other thing that I added is neutralization. See this capacitor I've added here? This is taking a little bit of out-of-phase energy and bringing it back to the grid. And that allows me to neutralize the 811A final, like a bridge circuit. This particular style of neutralization is not pure plate neutralization. For pure plate neutralization, it takes a differential capacitor here, and you have a perfect center tap. And it goes to the differential capacitor. This is called Hazeltine. Hazeltine is interesting because it uses a part of the coil, but not all of it. And none of the tuned circuit currents are going through this little tag end coil here. This is just to give us a little bit of out-of-phase energy that we bring back. That's a Hazeltine plate neutralization. It's a form of plate neutralization. Not as common as the center tap differential cap style, but it's nice because it allows you to use a simple capacitor rather than a differential capacitor. So here's the final schematic of what is actually going to be on my bench.
So I went ahead and did it. I actually built a power amplifier that's representative of the one that they used. Now I'm using a much smaller tube. It's an 811A, and I'm only using one instead of three 204s that they were using. So it's a miniature version of what they were doing. Now I still have the 211 as my Hartley oscillator. It's going to be driving this power amplifier. And the power amplifier, right now I'm setting it up to be resonant on the right frequency. So I have this coil that I took out of an old marine radio, It has plenty of inductance. With about 100 to 150 puff on this cap, it's resonating down at 1.82 megahertz in the 160 meter band. So we're looking at the coil right now, and I'm using something called Hazeltine Neutralization, which is plate neutralization. Actually, I'm down to about the quarter point on the coil. That's where I establish my ground, and that's the portion of the coil that's actually hooked up to the variable. This is the amount of the coil that I'm tuning, just this portion. This leftover portion down here, his only job is to establish a negative 180 degree signal that I take back through the neutralization capacitor to the grid circuit. It does not need to be exactly in the center of the coil. It just needs to have enough feedback to neutralize the stage. I don't need to have any special kind of capacitor either, because I'm just tuning this portion, and this part is ground right here. So this is kind of a clever way of doing neutralization where you don't need a fancy balanced differential type capacitor here, and you're just using a single coil. You're just choosing where to put the ground center tap, and it isn't in the center, it's down at about a quarter, and with about a 50 puff neutralizing capacitor, I'm able to neutralize this single stage. Now, what if I had 3 of them in parallel? Well, I probably would need to go closer to the center of the coil. I'd need a bigger coil. I'd need a bigger neutralization cap, because it looks like I need quite a bit of capacitance to neutralize this thing. So when you keep adding the stages in parallel, it's going to unbalance the bridge, and you're going to need a larger neutralization cap.
So I don't often get a chance to demonstrate transmitter neutralization, and this breadboard setup with the oscillator and the power amplifier gives me a perfect example of a system that could benefit from neutralization. You say to yourself, well, I hate neutralization. Every time they bring it up in the manual, it's some arcane method where I'm looking at the milliammeter and twiddling knobs and trying to figure out what I'm doing. I'm going to show you 2 very straightforward methods that you can use to neutralize almost any kind of transmitter, whether it's a tube, solid state, transceiver, whatever. The first is called the forward method, and you're actually using the drive in the transmitter, or in our case the oscillator, as the source, and you're doing some looking at the output with a scope or with a tuned receiver on frequency. And obviously you got to go through some attenuators if you're using a receiver. The scope in the AC mode with a 10x probe is usually okay on the output for this test. Then we have the reverse method, where we're using a signal generator, and we're actually going through a 50 ohm pad to establish a good 50 ohms into the output of the transmitter, and then we're looking at the grid of the final, or the plate of the driver, or oscillator in our case, and again we're going for the null with the neutralization capacitor. So first we'll do the forward method.
There's 2 popular methods. One of them is called the forward method, and this is where you disable the B plus in your transmitter and then perform the operation of neutralization, because you need to look at the output into a 50 ohm load, and you're going to be changing a neutralization capacitor and looking for the bridge to be balanced, or nulling the bridge. And the other is the reverse method, where you actually put a generator into the output port of the transmitter, and you look to do the nulling at the driver output, or the final grid circuit. Both of them you should have the B plus disabled. Okay, in forward neutralization, the filaments are lit in both stages. The oscillator is going to be activated. So if we were to look at this point right here, we would see some voltage coming off the oscillator. However, the B plus is off on the final. The final amplifier, the B plus is off. So before we do any neutralization, we want to make sure we're on frequency with the receiver, and we want to make sure that we have the frequency offset engaged. So why don't we fire up the transmitter and look at the output power first. It doesn't sound too bad. It's not perfect. So now we're going to do the neutralization. As you can see down here in the power meter, we have about 25 watts out. Okay, so we're going to kill the B plus on the final. And the note cleaned up. Okay, now I'm not going to change these settings. I'm going to leave them because those are the proper load settings on the output. I am simply going to attach the scope. Is the oscillator sneaking through the power amp. Okay, can you see that on the scope? Now we're going to key it. Now the next thing we're going to do is we're going to take our tuning stick and we're going to attempt to null the capacitor. Okay, that's the best we can do. So we should be neutralized now. When I'm neutralized, I'm not loading the oscillator as much, which is an interesting point. Okay. Okay, so next we're going to remove the scope. We're going to turn on the power amplifier's B plus and key the radio. Can you hear that it is cleaned up now? We've eliminated the chirp in the signal by proper neutralization. That is the forward neutralization method. So I am doing what's called backwards neutralization. I'm coming out of the generator on frequency, and I'm going through a 10 dB pad right into the output port of the amplifier. Then I'm looking at the grid of the amplifier. And I know that my oscillator is already on frequency, so I'm not going to touch that. The key is depressed, so I know I'm on the right frequency. Okay, let me turn this down. So I've got the neutralization cap hooked up, and immediately it's taken the amplitude down. It's starting to neutralize the amplifier just by connecting it, because it has a static capacitance, and that's already helping. Next, you rock the neutralization capacitor and try to balance the bridge or zero the waveform. So the point is, it sounded good without neutralization, but it sounds great with neutralization, so it just gives you that extra. The other thing it does is it eliminates the back wave that we were afraid of. Remember we were talking about the back wave that's coming out of the oscillator? Okay. The oscillator's going all the time, right? Here's the oscillator. He's going all the time. If we're not properly neutralized, look what's happening. We're putting out all of this crap into the air. But I was able to get a 211 over here as the oscillator and an ordinary 811 as the final. Even this setup is capable of probably 125 watts out of stable CW. It's absolutely amazing. Okay, let's load the transmitter. We start with the loading control, somewhat open. I've got it in the middle, not very much capacitance. The oscillator is on. Okay, we're dipping the plate. See where we're dipping the plate? And we're getting out almost 10 watts. Now let's bring up the loading. Okay, we're up to 20 watts now. Okay, bring up the loading a little more. About 22, 23 watts. Over 25, about 26 watts. That's about 90 milliamps. Approaching 30 watts out now. Not quite 100 milliamps. Okay, well, here's solid 30 watts. That's about the max. So we're kind of going backwards with our efficiency now. Anyway, it loads up just like you would a Pi network, except it's a link output. So load, dip, load, dip. And that's the way that we neutralized it, so it neutralizes best when you have it dipped. Wouldn't be any good if I didn't try to make a contact with this thing. Okay, it's a guy from the over the pond calling. That's kind of funny that the first call that I made would be to a G4 station. Okay, so the first station contacted on the Beast was over the pond, G4Z Charlie Golf. So I know what some of you are thinking, how could you possibly have that much luck? Sometimes, you know, you have the leprechauns, it's around St. Paddy's Day, you know, things can happen like that sometimes. I was using my 630 meter vertical, which is of course way low in resonance because it has center loading as well as top loading. So I put together a simple match it, and that was able to match that 630 meter vertical on 1.8 megahertz. That was a really noisy night, by the way, on stateside. We had a snowstorm coming in, and it discouraged people from even being on the band. So it was just lucky that Tony happened to be up early in the morning over in England to make the contact. So that was not too bad. That was a pretty good contact. Some pretty good luck there, getting over the pond, getting a transatlantic contact on my first contact with the breadboard. And there were some problems. I was sharing the power supply that I used to light the 811 and run the relay with the preamp on my receiver, and that was causing some of the noise from the transmitter to get right into the receiver. I was having to turn off the oscillator to hear Tony clearly, and of course that makes the oscillator cool down. Now it's got to warm up again. The other thing I had to do is I had to reduce my bandwidth on the receiver. I was using a couple kilohertz at first, and then I cinched it down to 400, 500 hertz type CW note, and now the transmitter was off frequency enough that it really sounded pretty bad. But believe me, it was putting out a good signal once I got the power supply, at least the current limit on the power supply from modulating. You might see that in the video. I had some issues, in other words, but we were able to make the contact. I was running the receiver with no TR switch. The receiver's hooked up to the amplified loop antenna, and the transmitting antenna is only about 20 feet away, going full blast. So it's a lot to ask for a receiver to be able to handle that kind of stuff, much less having crap coming in from the power supply. But we got through it okay. Hope you enjoyed this third video on the 1BCG transmitter. Keying, this one was focusing on keying, and a little bit longer video than I like, but I wanted to get everything done in this video so we didn't have to come back again.